A block is released from rest at point A, this point A, and slides down a curved frictionless track AB, that is this portion of the track, and then moves along a frictionless horizontal track BC, this is also frictionless, and finally moves up a rough inclined plane CD. So CD from here to D is rough. The coefficient of kinetic friction between the block and the inclined CD is 0.35. State in West the principle of conservation of mechanical energy. So this is a definition or a law that or a principle that we have to state, and we just go and then state it. It states that the total mechanical energy in an isolated system is conserved. That is 4.2 mechanical energy in an isolated system is conserved. And then we move to 4.2. That is use the principle of conservation of mechanical energy to calculate the speed of the block at point B. So what do we know? We know that at point A, this block is at rest. And then we also know that this surface is frictionless. And at point B, it continues to move. It has a velocity. So it means its velocity at point A, or a speed, is 0 because it's at rest. And then we have been asked to use a principle of conservation of mechanical energy to calculate the speed at B. So we go straight and then use the principle, and then that is the total mechanical energy in an isolated system is conserved. Now mathematically we say that the mechanical energy, which is the sum of potential and kinetic energy at the top of the slope, is equal to the mechanical energy at the bottom. So this is a principle mathematically, and when we put in the formula for potential energy, that is mgh plus the formula for kinetic energy, half mv square is equal to mgh plus half mv square at the bottom. So here, if you remember, we are not giving the mass of the block. Let's see, we are not giving the mass of the block. So when we substitute, what do? We write m as the mass, and then we say that m times g is 9.8 times the height, which is 5. We can go and check. That is from at point A is 5 meters high from the ground, and then we substitute the 5, and then plus 0. Now why 0? The velocity or the speed at point A is 0. So when you substitute 0 here, everything here becomes 0. It means that the kinetic energy at point A is 0, is equal to mgh plus half mv square at the bottom. At the bottom, that is point B, the height is 0, what is on the ground, and we substitute 0 for the height, and everything here becomes 0. Then we have half times the mass, we are not giving the mass, times the velocity square. So we find that there is m on the left hand side, and then there is also m on the right hand side. So when we divide through by m, then the m term will vanish, and then we have only numbers, and then an unknown variable, which is the v square. And when we use calculator properly, we'll find that the velocity or the speed at point B is approximately 9.9 meters per second. And then let's look at the next question, which is 4.3. Using energy principles, calculate the maximum height h reached by the block. Now, what we need to take note is that normally they will tell you using energy principles. Now, what are energy principles? Energy principles are basically two, and the first one is what we use in calculating this, which is a principle of conservation of mechanical energy, and which is applicable when the system is isolated. In other words, when there is no non-conservative force acting on the block. In other words, work done by non-conservative force is zero because there is no non-conservative force. And let's remember that non-conservative force can be frictional force, or it can be applied force, or it can be a tension. But in this case, the non-conservative force is not there. There's no friction, there's no applied force. This block slide under the influence of gravitational force only. Hence, here mechanical energy is conserved, and that is why it's appropriate to use the principle of conservation of mechanical energy. But what about point C to D? They say that it moves up C to D, and then we are given the coefficient of kinetic friction, which is 0.35. And then we were told earlier that CD, that is this plane, is a rough inclined surface, which means there's friction. So there is a non-conservative force, which means that the mechanical energy there is not conserved. We cannot use the principle of conservation of mechanical energy whenever there is a non-conservative force acting on the block. So what principle is available? And then that is the work energy theorem. The work energy theorem we can check from the formula sheet. Is work net is equal to change in kinetic energy. That is, work done by all the forces is equal to change in kinetic energy. Or we can say that work done by the non-conservative forces, the total work done by non-conservative forces, is equal to change in kinetic energy plus change in potential energy. So let's remember that either this formula, work net is called change in kinetic energy, or work done by non-conservative forces, either this can be used when there is a non-conservative force acting together with the conservative forces, conservative force. So we can select this one. I prefer to use this one. You can also try this one, and then let's see how we proceed. Now it is appropriate that we find which non-conservative force is involved by drawing a free body diagram. And that free body diagram is this. This thing was moving up the plane, and then we have frictional force acting in the opposite direction. Then we have the gravitational force acting, we have the parallel component, and then the perpendicular component, and then we have the normal force also. Let's remember that the applied force was not there because this thing was sliding. It was sliding. There was no applied force on it. So we have this diagram, which means that the non-conservative force that we have to concern about is the frictional force, and then we find the magnitude of it. So we say that Fk is equal to the coefficient of friction times the normal force. Let us remember that on the formula sheet for forces, whenever you are given the coefficient of friction and you are to determine the frictional force, we use this formula, which is frictional force is equal to coefficient of friction times the normal force. And then also, what information do we need that is not given directly? We also need the length of the incline, which is our displacement delta x. It is also not given, which means we have to look for that one also. So we need the frictional force and then the delta x, which we are not given directly, but we have information to calculate the frictional force. So let us see how to come out of this. Now, from the formula we have just seen from forces, we can say that Fk is equal to the coefficient of friction times the normal force, and then the normal force, let's remember, for on the incline is equal to the parallel component, sorry, the perpendicular component of the gravitational force. N is equal to Fg perpendicular, and Fg perpendicular is this term, which is mg cos theta, where m is the mass, g is acceleration due to gravity, and then theta is the angle of inclination. Now, when we check back, let's see what the angle of inclination. The angle of inclination is 30 degrees. So we are going to substitute 30 degrees for theta, and then see what we can get out of that. So we get Fk is equal to mu k times mg cos theta, and then Fk is equal to the coefficient of friction, which is 0.35 times the mass we are not given, times g 9.8 cos 30, and then we have Fk is equal to 2.97 times the mass newtons. So we have this as the frictional force, and then we also need to calculate the displacement or delta x, and here we use trigonometry, because if you check, we have the angle here. Now we need the height, that is what you are looking for, and before we can get this one, we need to get the hypotenuse, which is a displacement which we don't have. So it is appropriate to choose sine theta and say that sine theta is equal to the opposite of our hypotenuse, which is equal to h over delta x. And then let's see how to proceed from there. We say sine 30 is equal to h divided by delta x, and then we make delta x the subject of the formula, and then that gives us that is by making a cross multiplication, we'll get h is equal to sine 30 delta x, and we divide through by sine 30, we'll get delta x is equal to h over sine 30, which is equal to h divided by 0.5. Sine 30 is 0.5. Then we bring in the formula, which is the work energy theorem, and then that is work done by non-conservative force or non-conservative forces, if we have more than one, is equal to change in kinetic energy plus change in potential energy. And the only non-conservative force that we have there is the frictional force, and that is equal to Fk when we expand the work side times the displacement times the cosine of there's a mistake, s is missing, cosine of the angle between the displacement and the force is equal to half mv final squared, what that is the velocity at the top, minus half mv initial squared, that's the velocity at the bottom, plus mgh final, the height at the top, minus the height at the bottom. So here we substitute the magnitude of the frictional force that we calculated, which is 2.97 m, and then we substitute the the expression for the displacement, which is h over 0,5, which is this one, and then our theta is 180 degrees. Why do we say 180? Remember that this block went up, and then the frictional force is in the opposite direction. So the angle between them, the displacement up and then the frictional force, is 180 degrees, and it's equal to the final velocity, or the final kinetic energy, is 0. Why? Because we're told that this thing reached, when it reached point D, it stops where it reaches. Let us always remember that when they say for calculate the maximum height reached by the block, it means where it stopped. So when it stops, the final velocity is equal to 0, and then when we substitute that into the final kinetic energy formula, we get a 0, and then that is 0 here minus half times the mass, we're not given the mass, times the velocity at B at the bottom, which is 9.9, plus the mass times the acceleration due to gravity times the height at point D, that is this height, h, and then minus 0. Why do we say 0? Because this is the height at point C, which is the bottom of the incline. If you substitute 0 here, everything here becomes 0. And then when we simplify this expression, we are going to see that 2,97 multiplied by this is going to be 1 divided by 0,5, or 2,97 times 0,5 gives you 5,94. The m is there, and then h is still there, and then cos 180 is negative, and then so we get negative 5,94 mh is equal to, then this side, when we simplify this expression, where this term, we get negative 0,49 m plus, and then when we simplify this side, we have 9.8 mh, and then we can proceed, and then we say we have m term, and then m times m on this side, so we can factorize the m out, and then when we do that, we have negative 5,94 mh is equal to m into negative 49 plus 9,8h, and then this m will cancel this m out, then we are done with the m. And then when we go further, we have h term on the left hand side, another h term here. So what do? We group like terms. We move this 9.8 to the left hand side, it's positive, so when it comes here, it becomes negative, and then we are going to get 15,74, that is negative 5,94 plus negative 9,8h gives you negative 15,74h is equal to negative 49, and when we divide through by negative 15,94, we get h to be 3.11 meters. Please, this is meters as a unit. It is not the same as m as mass, so let us not be confused here, and then that is the solution for this problem. Remember, as I said earlier, you can also use this formula, which is work done by work net is equal to change in kinetic energy. Now, in which case, the work done by gravitational force will also be part of the network here, and only the kinetic change in kinetic energy will remain on the right hand side, and it will give you the same answer. You can try that one also.